I hope you all can see my screen, right? Guys, if you can see my screen, just let me know, please. Anyone? Any response? Okay. So in the last class, we discussed a lot of things related to this binomial distribution. Binomial distribution. We also solved a lot of examples also. So in this part, we will see some other distributions, especially like this Poisson distribution, geometric distributions. Obviously, we are just looking towards the basic of these distributions, and these basic things will allow you to actually solve all the questions that you want to solve. Okay, so starting with the Poisson distributions today. So Poisson distribution actually is a limiting case of binomial distribution. So like a binomial distribution, we had probability that x is equal to x. It was n choose x, p to the power x, and q to the power n minus x. So the basic definition of binomial distribution was that there will be some n number of repetitions. You have to repeat your experiment n number of times, and you are trying to find the probability of x number of successes. The success probability was p, and the failure probability was q, which is equal to 1 minus p. Okay, so this was the basic setup for us, and now we will see like how this particular thing, this particular Poisson distribution, actually the limiting case of binomial distribution. So we'll not go into the proof, but obviously we'll go to the intuition only. So talking about the Poisson distribution, so Poisson distributions is a limiting case of binomial distribution, and under the following conditions. So there are some particular specific type of conditions under which this Poisson distribution is regarded as a limiting case of binomial distribution. Like why this particular thing is important, because in paper sometimes you may be given some problems which will looks like binomial distribution, but actually we won't be able to solve this particular thing using binomial distribution. So in that case, we have to apply Poisson distributions. So I told ki in obviously the CMI paper, actually not everything is from very advanced level, but obviously these are the basic things which can be there. And like some binomial types of problem will be there, and you will think that you have to apply the binomial theorem, binomial distribution, but that thing will actually solved by this particular thing. Okay, so let's see what it is. So the following condition is that ki n, that is the number of trials, is indefinitely large. So let's say we saw that in binomial distribution we had n, which is the number of repetitions. So let's say if you're just tossing 10 coins or maybe just 50 dice, this is just as per means as this is just something that we can means term that this is a finite. But like sometimes the things go very large, like maybe 100 or maybe like thousand. So these type of things actually be termed as infinite in terms of statistics. Like in statistics, infinite actually does not means that it should be infinite. If any value is large, like maybe large, more than 100, more than 50, so compared to that, those things are actually also termed as like n is indefinitely large. So, like if we're talking about 10, 20, 35, something like n is equal to something like this. So that means you are talking about a finite thing, but obviously if n is like 1,000, 10,000, so those things are actually means very large. Okay. So in that particular case, the first condition is n should be very large. The second condition is that p, which is the constant probability of success for each trial, is indefinitely small. So it means that n is very large and p is tending to 0, means p is very small. So the two conditions you have now, n will be very large and p will be very small. So it may happen that let's say n is equal to 100 and p is equal to 0.001. So in this particular case also, like compared to p, n is very large. Okay, so this will be also considered the case of obviously the Poisson distribution. Okay, so the thing is that these particular two things are there, and the third thing is that if you multiply n into p, obviously n is tending to means n is very large and p is something that is p is something that is very small. So if you just multiply those two things, you will get a value, and that value we will term as lambda. Okay, so that will be the parameter of the Poisson distributions. So two things: n is going to be very large, p is going to be very small, and np is which is equal to, which is finite, is going to be some number, and that number will term as lambda. Okay, so that particular case, you can see that if np is equal to lambda, just we want that, let's say np is equal to lambda, then in that case p is equal to lambda by n and q is equal to 1 minus lambda by n. Okay, so obviously this particular thing, binomial distribution, under the binomial distribution in this particular thing, we have this binomial np is equal to ncx p to the power x to the power n minus x. And if you just put p is equal to lambda by n and q is equal to 1 minus lambda by n, we get this particular expression. And we know that we are trying to limit this distribution under limit n tend to infinity. Okay, so like in any statistics and probability, if you just see something like a limiting case or something like that, it means that some limit will be applied. So maybe here we want to find the limiting case of binomial distribution, and under the case that n is going to tend to infinity. So this particular thing in the binomial distribution, we will just apply same limit, and we get this particular expression. Now to solve this expression, actually it's a very calculative task. To solve this expression, you have to do a lot of calculus thing and apply a Stirling, some Stirling concept is there, some Stirling approximation. But that thing is not of our interest. But thing is that if this particular thing just that I will put there in the box, colored box, this particular thing will give rise to the this particular binomial Poisson distribution. So this derivation to from point this to this is actually two complex things. But things that this distribution, this Poisson distribution, actually comes from the limiting case of binomial distributions when n is tending to be infinity and p is very small. Okay, so obviously at the overall idea, we can just say that a random variable x is said to follow a Poisson distribution if it assumes only non-negative values and its probability mass function is given by what we got here. Okay, so this is e to the power minus lambda to the power x upon x factorial. Two things to be keep in mind: lambda is always going to be a positive number, and x here is going to be anything between 0, 1, 2, or till infinity. So anything means you don't know about particularly x. So x can be any number. It's not like like in binomial distribution we had x is equal to 0 to till n. Okay, but here the obviously n tend to infinity. That's why this binomial case has been turned into a Poisson distribution, and this particular thing is there. So two things to know, like if any particular thing is given, like Poisson distribution is given, so you have to use this particular probability mass function. And if a binomial distribution is given, some setup of binomial distribution is given, and it seems like that this particular thing can be solved by the Poisson distribution. In that particular case, you have to find this particular thing lambda and then use the Poisson distribution. So, like anyone have any questions regarding understanding the Poisson distributions and how these Poisson distributions arise? Any questions? Just let me know. And if it's clear, just let me know. Anyone? Okay. So if anyone don't have any other questions, then just let me move to some other examples, and then we will see like how these things can be useful to us. So first of all, the thing is that the like the in binomial distribution, the binomial distribution are being represented as B and P. The Poisson distribution is noted as P lambda. So if x is a Poisson distribution, so this is a more notation of binomial distribution, and the Poisson distribution x follow p lambda. P lambda means this is a Poisson distribution for p, and lambda is a parameter. So lambda is the main thing. The lambda here is the parameter, and in the binomial distribution we have n and p as the parameters. So these two things you have to keep in mind. Whatever the representation of particular distribution is going to be. Second thing is that this particular thing is going to be one. Obviously, we saw that na, ki for any PMF or any probability density function, you have to do the summation of x, probability of x is equal to x, it's going to be one. And in any real continuous distribution, the integration part from minus infinity to infinity, fx dx is going to be 1. Okay, so this thing, if you check out, this thing is going to be 1. And how this thing is that if you just do this calculation, then this particular thing will be sigma x is equal to 0 to infinity to the power minus lambda to the power x of x factorial. So this is the just same the Poisson distribution here, and this particular thing is constant with respect to the summation, so we'll just keep it out. And this particular thing is just the expansion of what is it? Expansion of e to the power lambda. So just two things multiply together and we get the one. So obviously for any distribution we can do this particular thing, that this particular thing is getting one, whatever the case is. Okay, so any distributions, whether it's a standard distributions or any distribution that you have you want to do, this particular thing is going to be one. Okay, so obviously at this point of time, just let's discuss some properties of Poisson distributions. So and then we will see some questions. Don't worry about it. So Poisson distributions occurs when there are events which do not occur as outcome of a finite number of trials or experiment. So like in binomial distribution, we were considering experiment which we are repeating n number of times. Okay, but in Poisson distribution we don't do like that. Okay, so just give me one second. I'm receiving some call. Okay, so obviously the thing is that in Poisson distributions, when there are events which do not occur as outcome of a finite number. So what this means is that in binomial distribution, we were trying to replicate our experiment when we were repeating the things n number of times, and we has the probability of success Ps defined. Okay. The thing is that this type of things actually does not happen with the Poisson distribution. So what is the real case? It occurs at a random point of time spaces wherein our interest lies in the number of occurrences of the event. So like let's say you are talking about a particular road, okay, and we're talking about number of accident. Uh, in a particular year. Okay, so let's say you have given that key in a particular day also. Let's say today is the whatever the date is 25th. You want to consider the number of accidents on that particular road. So obviously in Poisson distribution we always talk about the number of occurrences, not the number of non-occurrences. So we are not talking about number of non-accident. So that thing is not of our interest. So obviously in Poisson distribution, the particular thing is that we are always talking about the number of occurrences only. Okay, any random point of time. So maybe today, maybe tomorrow, maybe sometime else. So this is the just for the intuition only. Okay, these type of things you have to see as a uh, example of random Poisson distribution. Let's say you are given a book, okay, and you want to talk about the number of errors in a particular page of a book. So obviously, it's also about the number of occurrences, not the number of correct things about the book. That is not of our interest. Okay. So the thing is that anywhere between Poisson distribution, any examples, you will always talk about the number of occurrences, and that can be of any number of times. So let's say at hypothetically number of accidents can be infinite also, like 10,000, 1 million on particular road. But obviously that number is not possible, but that can be hypothetically possible. Number of errors can be large, very large. Obviously 10,000 error can also be there in no single page. Obviously that is hypothetically true, but obviously just we are talking about the number of occurrences only. So this is just for the intuition. The mean of Poisson distribution is given by lambda, the parameter that you have, and the variance of that particular random variable is given by the lambda square. So this is the mean and variance of the Poisson distributions, and their moment generating function is given by e to the power lambda e to the power t minus 1. So this particular thing is the moment generating function. So anywhere in the questions you see moment generating function of any distribution given like this, you have to consider that this is a Poisson distribution which follow the parameter which has the parameter lambda. So lambda will be any number. So lambda will be any number. Okay, it will be given, and the structure of the MGF will be something like this. Okay, so we will just see some examples like how we can use these particular rules to find calculate some of our questions. Okay, one thing is that like these derivations are too complex. That's why I've not included here. Obviously it's not of our interest. That's why you don't need not to go into the any derivations of this particular thing. Just remember any distributions PMF and their mean, their variance, their MGF, and obviously you should know what are their practical application and how to solve questions related to that. Okay, we'll see some questions, but let's just talk about the additive property of the Poisson random variable. So in additive property, we talk about that if xi, so let's say xi is from 1 to n are the n independent Poisson variates, independent Poisson variates. Okay, these things should be kept in mind. So if there are n independent Poisson variates, so x1 is a Poisson variable, x2 is a Poisson random variable, x3 is a Poisson random variable, and like that we have n number of independent Poisson variable with parameters lambda I. So for x1, this particular parameter is lambda 1. This x2 we have lambda 2. This x3 we have lambda 3, and like this we have n number of parameters and n number of uh, n number of independent Poisson distributions. Okay. The thing is that if you want to calculate the distribution of sigma xi, means you want to find the distributions of all summation of all this particular random variables, Poisson random variables. So this is also going to be the Poisson random variables and with the parameters summation of lambda. So let's say you want to find some Poisson distribution of x1 plus x2 plus plus xn. So these things are also going to follow the these Poisson distributions with the parameters sigma I from 1 to n lambda n. Okay, means lambda 1 plus lambda 2 plus lambda n plus dot of lambda n. So this particular thing is called additive property of the Poisson distributions. Simply is that if we have just n number of random variables, Poisson random variables which are independent and with their particular parameters as lambda I, then their summation is also going to follow Poisson distributions with the parameters sigma lambda high. Okay, so this is just a additive property that you need to understand. We also talked about the additive property of binomial distributions also, and that's why you need to understand this particular thing. Okay, so at this particular point of time, I'm just talking about the summation of random. I'm not talking about if the difference of the random variable is going to be Poisson distribution or not. This particular thing I'm not talking about. I'm just talking about the addition of random variable. Okay, so this thing should be kept in mind, and this is the rule. Okay, so, so at this point of time, if you have any questions, you can let me know, or otherwise we will move to the examples. Any questions you have, just let me know. Guys, do you have any questions? Just let me know, or if it's clear, just let me know. Okay, so let's just see some real life, means the real examples of the point distributions, how the things are going to be. So things that let's talk about examples. So a manufacturer of quarter beans knows that 5% of his product is defective. So he's talking about the defective his product and know that 5% of his product is defective. Okay, if he sells quarter beans in boxes of 100, okay, so means that he means things that he's trying to sell his quarter pins in boxes of 100 and guarantees that not more than 10 pins will be defective. So in a box he contains 100 pins, and if he just contains 100 pins in the box, he makes sure that not more than 10 pins will be defective. What is the probability that a box will fail to meet his expectations or guaranteed quality? Like when, let's say if a box is picked at randomly and that particular box has more than 10 pins defective, let's say 12 pin defectives or 11 pin defective or 15 pin defective, in that particular case he actually does not, his quality or his guaranteed quality is not actually meeting the expectations. So these particular things we have to find. Okay, so what will be the probability? So if you just want to see, you can see that we are talking about quarter pins will be, if probability of any quarter pins to be defective is 5%, means 0.05. Okay, second thing is that n is equal to 100, because we're talking about the defective pins among 100 pins that we have put in a box. So that thing n is equal to 100. So I told ki this can be solved using the binomial distribution also. But thing is that here n is equal to 100 and p is equal to 0.05. So comparative to this particular n, this p is very 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 small. Okay, so here you have to apply a Poisson distribution. So apply Poisson distribution means you have to find lambda which is equal to n into p. So you find lambda n is equal to n into p, which is going to be 100 into 0.05, and that is 5. Okay, so obviously I talked about the p is small, that's why we are using Poisson distributions comparative to 100. Okay, so if you do 100 by 0.05, it will give that so this particular thing is more than 2000 times than this particular p. Okay, so this particular say means in this way I told okay, this should be considered as the somewhere you just can't apply the Poisson distribution. Okay, can't apply the binomial distributions. Like case of binomial distribution is very simple. Now let's say you tossing 50 coins, okay, and probability of getting a coin is 1 by 2, so which is 0.5. So comparative to this particular thing, you can see that this is very large. This is very 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 small. 0.05 is very 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 small. That's why you have to just keep in mind where you have to use the Poisson distributions, or where you have to use the this binomial distribution. So in this particular case, now we know that our lambda. So just we to know that if x is a defective pins in a box and box of 100, then probability at x is equal to x. This is going to follow a Poisson distribution. So this Poisson distributions has the same format: u to the power minus lambda, lambda to the power x upon x factorial. Lambda is equal to 5 that we got. So we just converted this into this thing, particular thing. Now we are talking about what is the probability that we will fail to meet the expectations or guaranteed quality. So I thought if more than 10 pins are going to be defective, in that particular case, this particular thing actually is going to be failed the quality. So we actually are interested in finding that x, which is the defective number of pins, is going to be greater than 10. Okay, so this thing we can do it. So this particular thing we can do this way, and obviously this thing can be broken down into 1 minus probability of x less than equal to 10, because these two events are the mutually exclusive event. In that particular case, this thing is going to be summation. Obviously x is equal to 0 to 10, because this minimum x can go to 0, and we'll just find this particular summation. Okay, so in this particular thing, we can see that our probability of success is probability that e to the power minus 5 which come out, and this summation whatever you get. Okay, so obviously till point 10 you can't find the summation, so you can just leave your answer in this way. So this is how you just use the binomial approximation to solve the questions in the form of Poisson distribution. If you have any confusion or understanding any part, just let me know. Or if it's clear, just let me know. Yeah, 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 definitely. And yeah, so your point is right. And like certain at certain point you can means the things that okay, these type of things like especially in the probability and statistics, some concept of like every distribution has some assumptions, like binomial distribution has some assumptions, Poisson distribution has some assumptions, and how this particular thing is going to be means how binomial distribution is we going to be converted into Poisson distribution, that also has some assumptions. So obviously, if that assumption satisfy, you need to use Poisson distributions. Otherwise, you can use binomial distribution. So if their probability would have been, like 0.4 or 0.5, so it's a large number now. So here you have may have used that particular, uh, obviously the rand. Yeah. So in that this case, you have to keep in mind. Okay, guys. Any other questions you have? Anyone? Okay, so if you don't have any questions, just let's move to some another example of Poisson distributions. Here, six coins are tossed 6,400 times. Okay, so like this is the number that you have to put. So six coins are tossed 6,400 times. Using Poisson distributions, find the approximate probability of getting six hit R number of times. Okay, R number of times. So it's saying that ki there has been we took the six coin, so take six coin we took, and we tossed them 6,400 times. So once we tossed this six coin together, and like some coins may have been turned of head. Let's say this head, tail. So this particular thing may be there. Okay, so it's talking like 600, 6,400 times we repeated the same experiment. Then we have to find the approximate probability that we will get six head at least r number of times. Like let's say 100 number of times we may have get six head. So this particular probability you have to find. Okay, so let's say how we can apply the Poisson distribution. Okay, so obviously, if we're talking about the tossing the six head, so if obviously our required P is when we got the six head, and six head means probability of getting six head is 1/2 to the power six. This is fairly simple, and like if just we toss two coin together, then probability of getting two head is 1/4. Okay, obviously in tossing of six coins, the probability of getting six head will be 1/2 to the power six. Now, compare to this n number of times the experiment we had and the particular probability we had, this particular thing is obviously going to be this particular thing is going to be Poisson distributions because it's a very large thing. Okay, so we calculate this product of n into p. N is 6,400 and 1/2 to the power 6 is 64. So this particular case will we get lambda is equal to 100. So here we have to calculate means using Poisson distributions the required probability of getting six head r number of times. Okay, so x is a like what is the x here? X is equal to the number of heads that we get when we are tossing six coins. Okay, so in that particular case, x is equal to r. It means that we have got a six head r number of times. Okay, so in that particular case, this particular thing is going to be e to the power minus lambda to the power upon r factorial, and obviously we are trying to find into the terms of r. So just put lambda here and just leave everything in terms of r and get this particular probability. Simple thing, just like obviously when you find that n is very large and compared to p that you have, in that particular case we have to just convert everything into the Poisson distributions. Find the lambda, use the particular Poisson distributions. Obviously, don't forget what your x here is. So x here is the number of times you get head means six head if you are tossing coin. Okay, so I told like in Poisson distribution you have to specifically keep in your mind about the number of occurrences. Okay, what is the number of occurrences? Like this first case we saw that this particular x is the number of defective pins. So what is the occurrences here? In number of defective pins. Okay, in that particular case what is the occurrence? Number of getting six head when we are tossing this particular coin or six coin together. Okay, so you have to keep in your mind about the number of occurrences. What is the number of occurrences there? So guys, is any confusion regarding understanding this particular thing? Just keep in mind that x is equal to number of occurrences, and then you will have a clarity of your thoughts, like how to apply this Poisson distribution in this particular case. Any confusion regarding this? Okay, so let's now move to some other example also, some better examples of Poisson distribution. So things that in a book of 520 pages, so a book contains 520 pages, 390 typographical errors occur. It means that out of 520 pages, total number of errors that occurred in the page is 390 errors, typographical error, maybe some typo error or something like that. 390 errors there in total 520 pages, assuming Poisson law for the number of errors per page. So like obviously told, if you have a particular book and you want to find like what is the number of errors in particular book, that actually follow Poisson distribution. Obviously, because we are talking about a number of errors, number of occurrences here. So assuming Poisson law for the number of errors per page, find the probability that the random sample of five pages will contain no error. So it means that just assume that particular per page it's following, means obviously the error per page it's following Poisson distribution. Then you have to find a probability that if you just pick five pages, that will contain no error. I think someone mic is on. Okay, so it means that finding the probability that a random sample of five pages will contain no error. So just let's see everything step by step and we'll able to solve it. Obviously, in that particular case, we need to find the average number of errors per page. So 520 pages contain 390 errors. Okay, so average number of errors per page will be obviously 390 divided by 520, which is going to be a number 0.75. Obviously, lambda is equal to 0.75 because lambda is the parameters of your distribution, and this particular thing, average number of typographical error per page is going to be your lambda. In this particular case, if you use Poisson probability law, the probability of x error per page is obviously the Poisson distribution, because it's saying that you have to Poisson distribution. So e to the power minus lambda x, x factorial, and put the lambda here, and you get the this particular thing. Now we have to find this particular probability for the five pages. Okay, so let's say we are talking about means this particular thing, x is equal to zero. X is equal to zero means that any particular page contain no errors. Okay, x is equal to what x is. We have specifically written that x is the number of errors per page. Okay, so x here is that the your randomly chosen a page does not contain any error. So you put here x is equal to zero. So this particular thing is going to be one. This particular thing is zero factorial is going to be one. Okay, so we have just this particular quantity. Now this particular thing is that any pages that you picked at random does not contain any errors. Now we have to do this for the five pages. Okay, so there are five pages. So let's say there are page P1, P2, P3, P4, and P5. Okay, so in this particular case, probability that P1 intersection, P2 intersection, P3 intersection, P4 intersection, P5. So this means that P1 also does not contain any error, P2 also does not contain any error, and similarly P3, P4, 5 also does not contain any error. So these are the independent events. Okay, like obviously if you just pick a page at random and pick up second page at random, then obviously the number of occurrence of error in particular page 1 and page 2 does not have any dependence. Maybe there can occur five errors, there can occur seven errors. This does not depend on this first page or second page, third page. So these all are the independent events. That's how we just multiply the probability five times, and we get that the probability of picking a random sample of five pages will contain no error is equal to this particular things taken five times. Okay, so anything related to like how confusion, any confusion like how we do this problem or anything like that? Just simple thing, just we just find the lambda, which is the number of what you can say average error per page, and then we just use Poisson probability law, where x is the number of errors, x follow the Poisson distributions, which is the for single page. Okay, this is for single page. So x follow Poisson lambda. So x is equal to zero, small x is equal to zero means that any particular page does not contain any error. So we found this particular probability, and we want to model this thing for the next five pages. So we just like obviously any page is going to be just what you can say, just it's going to be just independent event, and that's why we just applied this probability five times, and then we got the desired result. Anything guys, any confusion, anything, just let me know. uh, Okay, so I told ki, like just let me just erase some part and just I'll be able to explain you better. And this is, like just you asked a good question because this thing will help you clarify your concept of Poisson distribution. So in the Poisson distributions, X is the number of occurrences. Okay, X is the number of occurrences. Here the number of errors per page. Okay, a number of errors per page. And we just saying that ki Poisson law for the number of errors per page. So means X follow Poisson distributions with parameter lambda, whatever the lambda is, and it's for the any single page. So you have first page that's also follow Poisson distribution. You have the second page that particular means finding the number of errors in the second page also follow Poisson distribution. So x is equal to 5 means there are 5 errors in a particular page. X is equal to 7 means there are 7 errors in a particular page. So we are talking about the errors in a particular page number. Okay, so let's say ki x is equal to 10. It means that any particular page that you have taken out at that point, it contains 10 errors, 10 typographical errors. So we are talking about find a probability that a random sample of 5 pages will contain no error. So let's just find that just random sample of one page, just to pick a page at random, and that will contain no error. So no error means x is equal to 0, right? So that's why we found x is equal to 0. It means that any random page that you find out that contains no error. But we are talking about the 5 pages together. So means like first page does not contain error, second page also does not contain any error, third page also does not contain any error, and these are all independent Poisson distributions. That's why we need to apply means this particular type things multiplied 5 times. Are you getting it? Yeah. Yeah, I mean, let's say anyone have found that okay, find a probability that any random sample of 7 pages contain exactly 3 errors. Okay, so we have found x is equal to 3 per particular page and did that particular thing 7 times, right? Exactly, exactly. Means so obviously all the events are means all the pages for all the pages it's going to be a separate Poisson distributions, and all those are independent. So like we just talk in the probability that now let's say there are two independent events, then probability of A intersection B is equal to probability of A into B, right? And same for the if 5 events or 7 events are there, same thing we need to apply. So these things 0. E to the power minus 0.75, this thing e to the power minus 0.75, and similarly. So is this thing clear now? Okay. Okay. So now let's move to the some means so obviously you can just solve some other question also, but let me just discuss the thing and I can so then we can start a geometric distribution. So like in Poisson distributions, you will see specifically questions of this type. Okay, some real life examples will be given. You have to apply something like this, some basic probability concept you have to apply, like independence of event or something related to like binomial approximation. So obviously a lot of different types of questions can also model, like find this thing, find that particular thing, find the expectations. So these things actually depend upon the doing intensive calculation. But in CMI paper, there you will not be means asked the intensive calculation. You will be asked only the things where you can just apply the basic probability law, things like that, and you can solve the questions. Okay, so here also just let's talk about this particular thing and these things that the x and y are independent Poisson random variables. Okay, independent means obviously probability of means if you are just saying probability of x intersection y or something like that, like obviously covariance of x y, and if x and y are independent, that thing is going to 0. So any two random variables that we encounter, it's if it's independent, then it's follow all the particular rule that we talked earlier for the independent random variables. So if we're talking about the covariance, that is going to be 0. If we're talking about the probability, that's going to be multiplied together. Okay, so this particular thing will be there. Okay, so just keep in mind that whenever we talk about an independent event, it follow the all the rules of the independent event. Okay, it is true. It is true in general. Okay. So just let's talk about the thing that we have given two relations. A probability that x is equal to 1 is equal to probability that x is equal to 2, and probability that y is equal to 2 is equal to probability of y is equal to 3. So means that for x Poisson variates, this particular thing is true, means given, and this particular thing given for the y. Then it's asking to find the variance of x minus 2y. Okay, so what this x minus 2y means, we want to find the variance. So that part is later. But first, this follow Poisson distributions. In that case, you need to find the parameters. Okay, so let's say for x is a Poisson distribution. Okay, so in that case, we have this particular distribution as the this particular format for the Poisson distributions. In that case, let's say lambda is the parameter, and for y, same thing will be there. But let's say we just can't assume same lambda now, because this thing is we have assigned for the x random variable. So let's say we keep mu with another symbol, mu, lambda, beta, alpha, anything you can say. So let's say mu is the another symbol for this particular thing, y distribution. So these both are the independent Poisson random variables. So using the relation one, just you find this particular thing, it means that probability x is equal to 1. So put x is equal to 1 here, x is equal to 1 here, you get e to the power minus lambda, lambda to the power 1 into 1, and 1 factorial means 1. So this particular thing you will get in the LHS. And the RHS, just put lambda x is equal to 2, so get lambda square e to the power minus lambda and 2 to the power, sorry, 2 factorial. Okay, so this particular thing is there. Okay, and same thing we get for the, just if you do same thing, probability at y is equal to 2 and y is equal to 3, we get same thing, just same thing for the similar thing for the y also. And we need to solve these particular two equations, they get lambda and mu. So just we solved this first equations, we got lambda is equal to 2, and we solved the second equations, we got mu is equal to 3. So anyone at this point of time may ask that why not mu is equal to 0, because here also lambda equates to lambda is equal to 0, why not this is true? So like we specifically talked that lambda and mu, whatever the parameters of the Poisson distribution is, that is always going to be greater than zero. That's why we got here lambda is equal to 2 and mu is equal to 3. Just simple thing, no nothing fancy you need to do. Just put the whatever the value you get for the Poisson distributions here, and you need to find the lambda for the x and mu for the y. Okay, any parameters you assume, I have assumed lambda only, just you can assume alpha, beta, or some other parameter also. Obviously, just you need to think that this particular thing just don't keep lambda both places, because both are not the same distribution. Both are the Poisson variates, but both lambda, both means x may follow like p 0.5, or y may follow p 1.5. So these thing, this the parameters can be different. Obviously, both are Poisson random variables. Okay, that's why we have assumed lambda and mu separately. The next thing is that once you got lambda and mu, we need to that the variance of x. What is the variance of x? We talked that the variance of x is going to be, like in the beginning itself, in the Poisson distribution we talked that this this particular thing, mean and variance actually is going to be lambda and lambda square. Okay, so this particular thing. Okay, so I think this should be 1 minute. Just let me just verify this particular details about Poisson distribution. I think it should be lambda only. Yeah, so like this particular thing, variance and mean of this particular thing is lambda only. So I think here I made some mistake. So like you have to correct this mistake. Just here there is no lambda square or something like. So this is not the correct variance. It should be mean is also lambda and variance is also lambda. This is the true result. Okay. So I will just just let me improve this thing in the notes only. And you have to just improve. If you just get this PDF notes, just I am just explicitly saying that you have to keep in mind that this particular thing is lambda only. So mean is also lambda and variance is also lambda. So may I have just made some typo error. Okay, so in this particular case, if we just know the value of lambda and mu, we know that the particular x random variable, this particular x random variable will have variance of 2, and this particular y random variable is going to have the variance of 3. Okay, so this part we are clear. Now we are required to find the variance of x minus 2y. Okay, so we need to find variance of x minus 2y. Okay, in this particular case, like I have did not taught you like what is going to be the variance if we're just trying to find the variance of two particular random variables. Just give me one more second. So in this case, we have a variance of x minus 2y, and let's see a variance formula in general. So let's say you want to find variance of alpha 1x plus alpha 2y. Okay. So in this particular case, it's going to be alpha 1 square variance of x plus alpha 2 square variance of y plus 2 alpha 1 alpha 2 covariance of x comma y. Okay, so this particular thing is the general rule for the finding summation of two particular random variables. Okay, if here it's minus, everything is going to be same, only this particular thing is going to be replaced by the minus sign. Okay, so if we just talk about x minus 2y variance, it means that variance of x, obviously it's 1, it does not mean anything. 4 times with this particular thing is squared, obviously alpha 2 is square, alpha 2 square variance of y, and minus this particular thing minus sign here, uh, 2 into alpha 1 into alpha 2. So alpha 1 is 1 and alpha 2 is 2. So minus 4 covariance of x comma y. But you know that this particular thing x and y are independent. Okay, so x, y, and y are independent. Then in that particular case, they are covariance is going to be zero. So this particular thing is not of our interest. So only variance of x minus 2y is being represented by variance of x plus 4 times variance of y. So variance of x is 2 and variance of y is 4 into 3, which is 12. So overall variance of x minus 2y is going to be 14. Okay. So simple things that just you have to keep in mind the variance formula. So variance formula in general is variance of alpha one. Sorry, just I told you this alpha one x plus minus alpha two y is equal to this particular thing. Okay, so this thing is the variance of summation or difference of the random variable. Just minus sign will be just get attached to the covariance part only. So we exclusively talked about the expectations and some of the like if you want to find some of the two random variables or three random variables, if you want to find expectations. So this thing we have already talked, and we talked about in general also. So variance part you have to just see it here. You just if you want to find the variance of difference or summation of two random variables, the same thing. But the coefficient here will be squared. This coefficient here will be squared, and the covariance part will be two times alpha 1 into alpha 2, whatever the coefficient is, and covariance of x comma y. Okay. If it is plus, it need to be plus. If minus, it need to be minus. Any confusion regarding understanding this particular questions or anything else? Guys, if it's clear, just yeah, just ask. Yeah. Yeah. Yeah, so whatever this particular thing is that, like told na ki if alpha 1 plus alpha 2 y, so here this coefficient is squared, this coefficient is squared, so there is not going to be any negative sign here. Okay. Yeah. So this is the coefficient of y only. So this is alpha 2. So yeah, this is the means general confusion only. Like if it's going to be x plus 2y also, obviously if x and y are independent, it's going to be a variance of x plus 4 times variance of y. So this thing is always going to be positive. Like whether whatever the sign is, this particular thing is going to be positive. And if it's a minus also, this is going to be the same thing. Okay, so if this part is clear, then actually we discussed a lot of things related to Poisson distributions, and obviously we did a lot of examples. And once you complete this probability section, we will just see some examples of the paper also. And like obviously when you need to solve the papers by yourself also, and once we complete the syllabus, we will have 2 to 3 classes or 3 to 4 classes on the paper itself. Just we will solve paper each day. But like if I just solve the papers for you, obviously it's not going to be helpful. Obviously I've solved a lot of questions, but sometimes you need to find your questions by yourself, just solve. And if you have any problem, just let me know. We'll discuss those things in the later part. So we have discussed binomial, Poisson, and these two things are there. But for the sake of understanding, we have two more distributions in the discrete part, which is geometric and hypergeometric. So these are both very simple distributions and don't need to consider anything else. So just let us talk about the geometric distributions. We have some 10 more minutes. Okay. So geometric distributions mean, suppose we have a series of independent trials. Okay, we have independent trials. So let's say we are tossing maybe anything. Let's say we have an arm. Okay, we are picking a ball. Okay, then if it's a red, we are just seeing it. If it's not a red, we just put it in the bag and then again pick a ball. Okay. So it's saying that suppose you have a series of independent trials or repetitions, and on each repetitions, the probability of success remains the same. That is p. Okay, so it means that let's say we have a ball. Okay, we have a ball, and there is a urn, so there is a urn, and there are three red ball and four black ball. Okay, in that particular case, we want to find, means we will keep picking a ball unless you find a red ball. Okay, unless you find a red ball, one red ball you want. So let's say first time you pick a ball and that ball is going to be a black ball. Okay, so what you do, you just pick the same ball again in the urn, mix the urn again thoroughly, and just pick again a black ball. Okay, so first case, the probability of coming a red ball was 3 by 7. So again, if you just experimenting it the second time, the probability of getting again the sixth ball, again getting a red ball, is going to be 3 by 7, because there are same number of balls. And you repeat this same thing again and again and again, unless you find a red ball. And at that particular time, we this particular thing can be thought as a geometric distribution, because each time probability of success is going to be the same. Okay, so this is the only criteria ki independent, the events are independent, and each time the probability of success is going to be same. Okay, so we will see like how can we solve questions of this type. But first of all, just understanding this distribution, we have a series of independent trials and repetitions, obviously repetitions, and each repetitions the probability of success remains the same. That is P. P is the probability of success, which remains the same throughout the trials. Okay, so why this particular distribution is important? So here we have the probability that there are X failures preceding the first success is given by Q to the power X into P. So let's say first of all P is equal to given, P is equal to given, and Q is equal to 1 minus P. That is also we have. So we are interested to finding the probability that there are X number of failures preceding the first success. So let's say we are tossing this particular ball wala case, and in this particular ball wala case, let's say we have three red ball and four black ball, and we are saying that okay, we are repeating the experiment. Let's say what is the probability that you get the red ball in the sixth attempt, in the sixth attempt. So sixth attempt, what does this mean? Sixth attempt. Sixth attempt means you just failed five times. Just did not get any balls for the five time. So x here is equal to five. So we need to find it there. Q to the power x into p. Probability of x is equal to x. Okay. So this particular thing q to the power x is equal to p. It means that what is the probability of getting failing? Failing means getting a black ball. So it is 4 by 7 to the power 5 into 3 by 7. Okay. So this particular thing is there. So it means that okay, we are talking about probability that there are X failures. We are talking about X failures before getting a first success. Okay, and this probability is given by Q to the power X into P. Okay, so overall the definition of random variable is a random variable X is said to have a geometric distribution if it assumes only non-negative values. If it assumes only non-negative values, and its probability mass function is given by Q to the power X into P. Okay, obviously x here is the number of failures before the first success. This is the main thing that you have to understand. Okay, so we'll just see some examples, but obviously the various terms, like just you can see that if you just put x is equal to 0 1 2 3, that you will get here that p, then p into q, then p into q square, then something like that. You can see that though these all terms are the geometric progression, so you will just have a geometric progression series. So these are the geometric progression. So that's why this particular thing is called geometric random variable. Okay, geometric distribution. So mean here is the q by p, and the variance here is q by p square, and these are both the correct thing. And my moment relative function is p by 1 minus q into e to the power t. So these things are the basic properties, basic things related to the geometric random variables. So like just let's talk about the example. Obviously, like simple example, simplest distribution it is, and the example will be obviously something like that. You want to find the probability of something, some success after some amount of failure. Okay, so if the probability that a target is destroyed on the any sort is 0.4. So let's say you have a target, you are just shooting on the target, and it's saying that that particular thing is getting destroyed on any sort. So let's say fire the first shot, the probability of getting it destroyed is 0.4. What is the probability that it would be destroyed in the sixth attempt? So it would be destroyed in the sixth attempt means you failed for first five times. We did not hit the target for the first five times, and then at the sixth attempt we just hit the target. So it means that this particular thing is if we just fire for the first time, it did not hit it. So obviously probability of not destroying the target is 0.6. Second time you did the same thing and it happened with you for the five times, and then at the sixth time you did destroy the target. So this will follow geometric distribution, which q to the power x into p, and x is the number of failures. So number of failure is 5, obviously because you are destroying the target in the sixth attempt. So this thing is obviously q to the power x 0.6 to the power 5 into 0.4. So guys, anything understanding this simple random variable, geometric random variable or geometric distribution? Simple thing, just you need to find the probability of failure, obviously probability of first success, and before first success you have, let's say you get a success in nth number, nth trial, then obviously you have to fail for the first n minus 1 number of times, and that particular thing is q to the power x, whatever the amount of times you fail into probability of success. Anything related to confusion, anything related to understanding what's how this thing is working or anything, repeat skill, just let me know. Okay, so like same thing will be there. Like any examples, you pick same thing will be there. So let's say let's talk about this example. Just you can solve it using your own, but let me just talk about it. So a male couple decides to have a children until they have a male child. Okay, obviously we are talking about let's say there's a female child did not take into consideration. Then again a female child we did not take into consideration, and we keep it doing obviously if you get a male child. Obviously, like these type of things actually happens in the Indian family. So obviously I'm not commenting about that, but thing is that let's say assume this particular situation. So a couple decides to have a children until they have a male child. What is the probability distributions of the number of children they would have? Okay, so this obviously the probability distribution will be geometric random variable. If the probability of a male child in their community is 1.3, so let's say P is equal to 1 by 3, obviously then this particular Q is going to be 2 by 3. Okay, so how many children are they expected to have before first male child is born? Okay, so in this particular case, like you have to find the expectation of X here, because obviously X is the your a geometric random variable. So you know that in geometric random variable case, we have expectation of X is equal to Q by P. So is equal to Q by P. Okay, so because like there, it's not talking about the probability, it's talking about expected to have this number of children. So expected Q is equal to 2 by 3 here, and P is equal to 1 by 3. So in that case, it is equal to 2. So means on an average, you can say that if the probability of male child is in the community is 1 by 3, then how many children they have to expected to have before their first male child is born. So obviously 2 is the answer. Obviously, I'm not telling about the truth fact, but this is the answer that you get by this particular question. So obviously, like any particular, like let's say they are talking about the Poisson random variable itself. They're talking about, okay, how many error can someone get if he means someone something like expected value. So let's say what the expected number of errors per page, and this particular thing is going to be the lambda. And obviously we saw that, like here you can see that in this particular thing we find expected number of errors at the lambda itself, which is the average number of errors per page. Okay, so this particular thing is there's you can solve this particular questions using the geometric distribution. And anytime you realize that some particular probability of success is taken at the nth time, and before that we are talking about a long lot of failures, means all the failures are there. So these type of things actually we can model using the geometric random variable. Same other examples you can also see this particular example of this type. Here, a die means obviously the playing dice. Okay, a die is casted six until six appears. So it's a die is thrown. Okay, a die is thrown, and it is casted until the six appears. So let's say one is there. There's sometime two is there. It is again being casted until the six appear. What is the probability that it must be casted more than five times? It means that you are expecting to get a six if means you are not getting any six for the first five times. You maybe get a six for the sixth time, maybe seven times, maybe eight times. It means that this particular x is going to follow a geometric random variable, and this particular thing probability x greater than five is going to be your required probability. Okay, so obviously simple thing, a die is casted six times, and what is the probability that it must be casted more than five times? So it means that you are does not getting six in the first five times. You may get six in the six times, seven times, eight times, nine times, maybe till infinity. Okay. In this case, what you need to do, you need to find this particular probability. Obviously, like finding this particular probability may be translated into this way. Obviously, this you can write a simple thing, like from x is equal to 6 to infinity, and p to the power q to the power x into p. Okay, this particular thing is there, but obviously you can just solve it using the other way also, and just translate this following probability into this way: 1 minus probability of x less than equal to 5. So it means that sigma means this particular thing is going to be random variable. Okay, and this is you have to add for the from x is equal to 1 to 5. Okay, so 5 to the power 6 means q to the power x minus 1 into p, and same thing you have to do. So in this case, like you can find this variable. Obviously, if you put x is equal to 1, you get 1 by 6 only. If you put x is equal to 2, you get some other variable also. Until the 5, you can count that particular number. But this particular from x is equal to 5 to infinity, 6 to infinity, you cannot calculate this particular thing. Okay. So obviously, simple thing, just easy thing is that there is no any complexity. Just you need to find everywhere the this q to the power x minus 1 into p. So any confusion regard understanding any particular questions or anything else, just let me know. Guys, anything, if anything is there, just let me know. Please say anything. Okay, I cannot hear you. Okay. Yeah, yeah, yeah. I heard you. Okay. So obviously most questions in your thing will be from the binomial and Poisson also, but obviously geometric and hypergeometric is some related distributions that you should know at least. Okay, and obviously in future they may be, because if they have not written that key, we cannot ask questions from this particular thing. So obviously this thing will be there, and obviously if this thing are there, we have to solve this particularly this way. Okay, hypergeometric distribution, just one more distribution, and it's just a single phase thing. Just let me discuss. So let's say you are having a urn. Okay, you are having an urn. Okay, you are having an urn, and it has n balls. Okay, it has n capital number of balls there. Okay, now m of which are white. So out of this particular n balls, so out of their n balls, okay, n balls, m are white, m are white, m white ball. Okay, and n minus m are red. So this particular n minus m are red ball. Okay, then what we need to do? Suppose that we draw a sample of a small number of n balls at random without replacement. Without replacement means you know what? Just take a first ball, then you are not putting that ball again. You are just again drawing a ball. So that thing will actually reduce the number of balls in the bag or box. So things that we are drawing a sample of a small number of n balls at random from the urn. Okay. Then the probability of getting k white balls out of n is okay. So let's say you are talking about randomly picking a small n number of balls out of n. Okay. Okay, a small number of n number of balls out of n. So what is the our required area of discussion? Our required area of discussion is that you have to find the probability of getting k white balls. Okay, k white balls out of n. So obviously the thing is that you have to capital N number of balls, m are white balls and n minus m are red balls. This thing you know in prior to experiment. Okay, and you are just drawing a small number of n balls. So let's say capital N is equal to 100, then maybe you are drawing a small number of 20 balls. So you are trying to find a probability of getting k white balls out of n. K white balls. Okay, so you know that if there are total m white ball, then you have to choose k white ball up among that, and out of all obviously n minus m ball that you have left, you need to choose, you need to choose n minus k red balls. Okay, so this particular thing is that, and total number of selection can be, total number of selection can be, total number of n balls are there, so n choose n. So this is your required probability, and this is called a hypergeometric distribution. Simple thing, obviously the names thinks that it's something hyper or hyperparameter, but nothing like that. Simple thing is there. You are having capital number of n balls, and m are white and a small n minus m are red, and at that particular time you have to find, if you're just drawing a small number of n balls, you have to find what is the probability that there are k white balls, k number of white balls. Okay, so if n is the small n is the 20, then you are maybe interested in k is equal to obviously 0.10, or k is equal to 5. So simple thing, out of m white balls, how many balls you have to choose? You have to choose k white balls, and now you have n minus k balls to choose, and obviously these are going to be the red, because we have to find exactly k number of white balls there, and this to be n minus m, choose n minus k, and like nck is also represented by nck, and this is just like nck, and this is just a bracket thing. So this thing is the same thing, nck or nck. This is the also written nck, or it's a combination thing. So n minus 1 choose n minus k, and obviously what is the sample space? Sample space is out of n number of balls, you have to choose a small n number of balls. This is your sample space. So this is the required probability of getting a k number of white balls in case of this particular experiment. Guys, any confusion, anything, just you did not understand the simple thing, just if you have any confusion, any silly questions also let me know. Actually no question is silly questions. If you have any confusion regarding understanding any basic thing, just let me know. Anything, guys. If it's clear, just let me know. Yeah, yeah. Is anyone asking? Okay, and at this point of time, like obviously, for this hypergeometry, this mean and variance is not of our interest. Such a long equation is there. How means these things are just for the sake of your knowledge. Don't need to remember this particular thing. And obviously, if the questions will be there, it will be based on this particular setup only, and no mean or variance concept will be asked, because obviously these things are some complicated problem. But obviously, if you want to remember, you can do it for yourself. Obviously, at this point of time, just you should know this particular thing is that the hypergeometric distributions tend to binomial distributions when n capital N tend to infinity, and m by n, this particular m by n tend to p. Okay, so this is just for the sake of information, but I don't know how to utilize this information to solve any particular questions. But this is fact that this hypergeometric distributions tend to binomial distribution, and the condition is n tend to infinity, capital N, and m by this particular m by n is tending to p. Okay, so this is just a fact, and maybe just you can utilize this some fact somewhere else, but obviously I don't know till now how to utilize this fact. I did not find any questions based on this also. So just fact this you need to know. Okay, let's just see a simple examples based on the same setup. Setup will be just same. There will be some capital N, there will be some small n, then there will be some small number of sample, then there will be something k. Okay, same setup will be there. So just this should be our last point of discussion today. So a taxi cab company has 12 ambassadors and 8 Fiats. You know, like the ambassadors and Fiats are the car. So let's say a taxi company has 12 ambassador and 8 Fiat. So he has 20, total 20 number of cars he had. Okay, so he just rent the car. If five of these taxis cabs are in the shop for the repair, so like for the among the 12 ambassador and 8 Fiat, any number of five cars are in the repair mode. Okay, so maybe two Fiats or five three ambassadors or anything like that. So total 20 number of cars. So capital N is equal to 20 here, and you have five number of cars in the repair section in the shop for the repairs, and ambassador is as likely to be in the repairs as a Fiat. It means that the ambassadors can be also among those five cars, some ambassador, and some Fiat's car can also be among those five repair cars. Okay, so we need to find some probability. So first is that what is the probability that three of them are ambassador and five of them are Fiats. So obviously our interest of where n is equal to small n is equal to 5. So it's asking that what is the probability that three of them are the ambassador. Oh no. So obviously, simple thing. Just if you don't understand the hypergeometric distribution, also you can just solve it by basic intuition. Among the 12 ambassador, three ambassador you have to choose. Okay, and among the eight fiats you have to choose rest two, take two fiats. Okay, multiply by, and how many cars you had to choose means total sample space. Obviously, it was a 20C5 because among the 20 car you have to choose the five car. So this is the required probability of this. Success. Okay, same thing just you can do by your intuition. Okay, it's saying that at least three of them are investors. So three of them investor means one this will be three, then again it will be four, then again it will be five. So it means that you have to take it three. Then if it's a three, then it will be a five minus three. If it's a four, it's a five minus four. Obviously, so this summation thing actually justify what is your answer. And the next question is all five of them are the same make. Same make means either five of them are the fiat or five of them are the ambassador. So let's say if all five of them are the ambassador, obviously you have to choose 12C5. Okay, and this 8C0, it's going to be 1. Okay, so 8C0 is going to be a 1. Okay, and then 12C5, or either of all other fiats car, then 12C0 is going to be 1, then 8C5 or 1, 20C5. So like this is just you can say that the advanced thing related to what you can say. This thing is the advanced thing related to permutation and combination type questions. So generally permutation and combination type questions is solved it this way. Okay, it's solved it this way. So obviously hypergeometric distribution is just the name that we have tagged for a particular thing, which obviously choosing something out of the given choices, in number of choices that we have. So I will just advise you to just go through the PDF once again, and obviously just make the correction that okay, this particular place at this particular place, what is there. This variance is just the lambda, not the lambda square. Just you make this correction among your side. And I think we have discussed all the discrete random variables, right? Discrete distribution that we have, binomial, the Poisson, the geometry, the hypergeometry, and I think these are the enough for your CMI syllabus. And from the next class, we will discuss some more continuous distribution.